Okay, then we're in question 1 on the axis. Sketch the graph of 2x minus 5 times x plus 3 times 1 minus x, stating the intercepts with the coordinate axis. Okay, well, the first thing to notice here is that we've got a cubic graph, and cubic graphs, if they're positive cubic, so if we've got a plus x cubed, they're going to be sloping upwards like that. If we've got negative cubics, negative x cubed, then they're going to be sloping downwards like that. Well, what have we got here? We've got a 2x times by an x, so that'll be 2x squared. But then we've got a negative x here, so that would be negative 2x cubed. So this is a negative cubic, and so we know the graph will be sloping down like that. That's the first point. The next point is to find the intercepts. Well, where do we get intercepts? We could say the x-intercept is when y is equal to 0, right? Because the y coordinate is always 0 everywhere along the x-axis. And so we're solving when this thing here is equal to 0, which means that either 2x minus 5 is equal to 0, or x plus 3 is equal to 0, or 1 minus x is equal to 0. Now, I'm just doing that nice and slowly for those of you who have never really fully understood this. If this whole thing here is equal to 0, we've got 3 things that multiply together to give 0. And the way that works is if either one of those things is 0. So if you think about it, 5 times 0 is 0. 0 times by 5 is 0, right? So if we multiply 2 or 3 or 5 numbers and the outcome is 0, it means that one of those things is 0. So either this, or this is 0. And if 2x minus 5 is equal to 0, that means x is 5.2. So that gives us x is 5.2. 5.2, sorry. This one will give us x is equal to negative 3, and this one will give us x is equal to 1. So we want to indicate that on the graph. So I don't know, 1, 2, 3 there. 1, 2, 3. So where will our x-intercepts be? 5.2 is 2.5, so that's going to be there. 5.2. Negative 3 is over here. That's negative 3. And x is equal to 1 is there. So that's x is equal to 1. Okay, and then we want to find out the y-intercept. So the y-intercept is going to be when x is equal to 0. For the same reason, the x-coordinate is always 0 everywhere on the y-axis. So let's substitute in x is equal to 0. We will get y is equal to 0 minus 5 plus 0 times by 3 plus 1 minus 0. So we're going to get there negative 15. And so I'm going to indicate that down here. I mean, it's going to be difficult for me to draw that to scale, so I'll put negative 15 like that. Okay, and so then the job is just connecting the gaps, really. So let me, I'm just going to get rid of all my working, just so that I can fit my graph on. Of course, good idea for you to keep your working. So I've got to go down like that. Oh dear. So go down, go down, go down. Okay, let's turn back up. Turn back up. Like that, and then come back down through here. Right, so if we know the... sorry, I don't like this part here. Let me just change that. Okay, basically, if we know our x-intercepts and we know our y-intercepts, we know the general shape of the curve because it's a negative cubic, then we can piece together that information and we're going to get the graph as shown. Okay, next part, part B, hence solve the inequality, blah, 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 is less than or equal to 0. Well, the key word here is the word hence. Hence means we've got to use the information from before. So when is this going to be less than or equal to 0? Well, it's the same thing as saying when is the y-coordinate less than or equal to 0? Well, the y-coordinate is less than or equal to 0 here, all of that part, and here, isn't it? Right? So let me just highlight that on the graph. So we are interested in values of x between here, let's use a different color, I think, between here and everything beyond here. Right, so we can then write this and say the solution is going to be x is greater than or equal to -3 but less than or equal to 1, and x is greater than or equal to 5.2. Okay, so those two inequalities will define this part of the graph here and this part of the graph here. All right, next part. Is there any other part here? Yeah, part 2. On the axis below, we want to sketch the graph of the modulus of this function. Okay, well, what does the modulus do? If the value inside the modulus is positive, there's no change. But if the value inside the modulus is negative, then the modulus turns it into a positive, right? So the example is, let's say we've got the modulus of 4. 4 is a positive number, and so there's no change. But if we did the modulus of -5, -5 is a negative number, and so the modulus turns it into a positive, okay? So if we were to look at our original graph, right? Basically, everywhere where the y-coordinate is positive, there's going to be no change, right? Because that means that this value here, this whole thing, is a positive number. So whenever the y-coordinate is positive, the modulus is going to remain unchanged. So the graph is not going to change here or here, right? Where will the graph change? The graph is going to change in this region here, where the y-coordinate is negative, and this region here, where the y-coordinate is negative. And what will the modulus do? The modulus will take these negative values and turn them into positives, right? So let's imagine this point here is -15. When we modulus -15, we're going to get +15. And the same with every other coordinate on the graph, right? It will be flipped, basically, in the x-axis. So what we're going to do is we're going to say, okay, so I'll do it on this graph, right, just for simplicity. That will be +15. Okay, so I'll draw it on the other side, because otherwise it kind of looks like -15, doesn't it, right? This guy here is +15, okay? And so this part of the graph is going to stay the same. That's the same, okay? This part of the graph's the same, so that's the same. But everywhere else is going to be reflected in the x-axis. Okay, so I'll try to draw that as best I can, like that, like that, like that, and like that. Okay, so this thing here, if I get rid of all the blue, that will be my modulus graph. Okay, so it's basically all the values of the graph that were below the x-axis get reflected. Okay. Okay, then question 2, we want to evaluate this integral here. We must show all of our workings. So let me just rewrite that. We're going to integrate between pi/3 and pi/2 cos of 1/4 x. I always prefer to write it like that as some constant times by x. I find it a bit easier. Now, if we integrate cos, what will we get? We will get sine. So we're going to get here sine 1/4 x. And we always take the coefficient of x here, and we've got to divide through by that, because remember, when we're differentiating, we're using the chain rule, we would multiply by 1/4. We're integrating. Integration is the reverse of differentiation. So instead of multiplying by 1/4, we divide by 1/4, and dividing by 1/4 is the same thing as timesing by 4. Okay, so we're going to be doing that there, and then between the bounds of pi/3 and pi/2. Now, for those of you who are not sure about why cos integrates to give sine, then let me try to explain why. Let's think again about differentiation. If I have got the function y is equal to sine x, and I differentiate it, so I find dy dx, then what do I get? I get cos x. And what that means is that if I was to integrate cos x, what I would get is sine. Why is that? Well, because integration is the reverse of differentiation, right? So if differentiating sine gives me cos, then integrating cos will take me back to sine. In the same way, if I was to have the function y is equal to cos x, and I was to differentiate that, I would get negative sine. So what would that mean? If I was to integrate negative sine, I would go back to positive cos. And so and now imagine instead of positive cos, I was to differentiate negative cos. If I differentiated negative cos, I would get positive sine, because it's like I'm multiplying through by the constant -1. And so if differentiating negative cos gives us positive sine, then that means if I was to integrate positive sine, I would go back to negative cos. So basically what I'm trying to tell you is that you don't have to memorize a whole bunch of rules actually. If you can memorize how to differentiate sine and cos, then implicitly you already know how to integrate, because integration is just the reverse of differentiation. Okay? Now then, let's substitute our values in. So we're going to substitute in the upper bound, pi by 2. So if we do that, we're just going to be nice and patient, do it nice and slow. We will get 4 sine pi by 2 times by a quarter is going to be pi by 8. And then if we substitute in the lower bound, we're going to get 4 sine pi by 4 times by pi by 3. Sorry, 1 upon 4 times by pi by 3, which is going to be pi upon 12. Okay, so I think what we've got to do now is we've just got to substitute these values into our calculator. So let me just get my calculator. Okay, and I need to make sure that my calculator is first set to radians mode, right? So hopefully the pi should be an indication to you that you're using radians, but another important thing is that you are using differentiation or integration. And in differentiation and integration, you must use radians, right? You don't have any choice, okay? You have to use radians. And the reason for that is that the proofs for differentiating sine and cos require the use of radians, okay? So if you're doing a question where you're differentiating or you're integrating a sine or cos or tan, your calculator must be set to radians, and I suggest you do that right at the beginning. Okay, so I'm going to do sine of pi over 8, okay, minus sine of pi divided by 12, hit the equals button, and I'm going to times that all up by 4, and what I get is 0.495 to 3 significant figures. So 0.495 to 3 significant figures, and the mark scheme says that that is indeed our answer. Okay, all right, so let's move on to part B then. We want to find this integral. So here we've got an indefinite integral, so there are no bounds to substitute in. And the key thing to recognize is that these two terms are going to integrate differently. Okay, so the first term is going to integrate to give a ln, a natural log, whereas this term here is going to kind of integrate the normal way, because I'm going to rewrite it. Just rewrite it for you. So the first term, I'll keep it the same, 1 upon 4x minus 3. But this term, I'm going to rewrite in indices form as x to the power of negative 3 dx, okay? And essentially the rules that you need to remember are, if I integrate 1 upon x dx, that gives me the natural log of x plus c, right? So 1 upon x, or x to the power of negative 1, differentiates in a way that is different to x to the power of 2, 3, 4, 5, or 6, or even x to the power of negative 2, 3, 4, 5, or 6, right? It's a special case. And in the exams, what they love to do, they do this all the time, is they like to give you these two things together in one integral in the hope that they will trick you, right? And the most common trick, the common mistake the students will make is they'll have, like, let's say x to the power of negative 1, they integrate that dx, and then they try to do it the normal way, so they add 1 to the power, which gives 0, and they divide by the new power, which is 0, and then they go, what's that? Okay, if ever you've got this in an exam, you're doing this, you need to stop and say to yourself, hang on, I've gone wrong. This integrates with a different way. It integrates to give the natural log. Okay, all right, so now let's actually integrate it. Okay, so if I integrate 1 upon 4x minus 3, I get the natural log of 4x minus 3. So the thing on the denominator just goes inside the natural log, but then I take the coefficient of x, which is 4, and I divide through by 4, right? For the same reason as in part A, when we're integrating, we basically divide through by the coefficient of x. For this one, what do? Well, I add 1 to the power, so I get x to the power of negative 2, right? Not negative 4, because if I add 1 to negative 3, I go up to negative 2, and I divide by that new power, so I divide by negative 2 like that. And I need to remember the constant of integration because this is an indefinite integral. Okay, so let's tidy this up a bit. I've got 1 upon 4, the natural log of 4x minus 3, plus, not plus, sorry, because we've got a negative, don't we? Negative 1 upon 2, x to the power of negative 2 is 1 upon x squared plus c. Okay, and so actually we could rewrite that term as negative 1 upon 2x squared. That would be a totally acceptable way of doing it. Okay, let's just check the mark scheme. Yeah, they don't even require you to simplify it. The second line here, that would have been a perfectly adequate answer for the mark scheme. All right, then question 3, we want to determine whether or not this equation here has 2 distinct roots, 2 equal roots, or no real roots. Well, and this thing here should indicate to you that we're talking about the discriminant, right? The discriminant is the value of b squared minus 4ac in a quadratic, and this thing tells us how many roots a quadratic will have, okay? So the discriminant tells us the number of roots. Now, there are 3 cases that we need to understand. There's either the case where b squared minus 4ac is negative, where it is positive, and when it is 0. Now, if b squared minus 4ac is negative, that means that we have got no roots. If b squared minus 4ac is 0, it means we've got 1 repeated root. And that's important there, 1 repeated root. But if b squared minus 4ac is positive, it means we've got 2 distinct roots. We've got 2 roots which are different. Okay. Now, if you're wondering why that is the case, it goes back to the quadratic formula. The quadratic formula, the solution for a quadratic, is minus b plus or minus the root of b squared minus 4ac all over 2a. And what you should notice is that the value inside the square root there is the same thing as the discriminant, right? The b squared minus 4ac is the thing inside the square root. Well, if that term there is negative, it means we can't square root it, right? Because we can't square root a negative number. That means there are going to be no roots. There are no solutions to this, or no real solutions, okay? You'll find about that a bit more when you do your A-level. There's something called complex solutions, but we'll ignore that for the time being. If this term here is 0, however, then what we're going to get is we're going to get minus b plus 0 over 2a and minus b minus 0 upon 2a. Well, that's the same thing, isn't it, right? It's going to be minus b upon 2a twice. So we've got the same solution, but 2 times. And so we say we've got 1 root, which is repeated. Or sometimes people say we've got 2 roots, which are the same, right? But I hope you can understand that that means the same thing. We've either got 1 thing that's repeated, or we've got 2 things which are the same, right? It's the same thing. Now, if the discriminant is positive, let's say it's 9, right, positive 9, then if we square root that, we're going to get minus b plus 3 upon 2a, or minus b minus 3 upon 2a, which means we've got 2 distinct roots there. Okay, so that's where that's coming from, guys. All right, so hopefully that's a quick recap for you. Now, let's try to actually do this question. So we got to rearrange this basically. So I'm going to, right here, we're going to get 4x plus 1 times by 3x plus 2. And I'm going to multiply through by 5x minus 3 on both sides. We get x plus 1 times by 5x minus 3, which is 12x squared. So we expand the left-hand side bracket, plus 8x plus 3x plus 2 is equal to 5x squared minus 3x plus 5x minus 3, okay? And I'm going to bring all the terms to one side, so I will, actually I'll simplify this one first, I think, because I really don't want to make mistakes. It's so easy to make a mistake. So I'm just going to be nice and patient, at least as a demonstration to you, right? Also of the value of patience. We want to be careful more than we want to be quick. Okay, so now I'm going to subtract 5x squared from both sides. That gives me 7x squared. I'm going to subtract 2x from both sides. That's going to give me 9x. I'm going to add 3 to both sides. That's going to give me 5. Okay, so now this is a quadratic, isn't it, right? A quadratic where the value of a is 7, the value of b is 9 and the value of c is 5. So we're now going to calculate the discriminant, b squared minus 4ac. So b squared minus 4ac. So we're going to get 9 squared is 81 minus 4 times by a, which is 7, times by 5, which is our c. Okay, so we're going to get 81. Okay, well, look, 4 times by 5 is 20, isn't it? And 7 times by 20, well, we can do 7 times by 2, which is 14. Double times by 10 is 140. And the key thing you can tell about that is that that is negative, isn't it, right? It is 59, is it? Yeah, 59. Hang on, I'm just going to use a calculator because I sometimes go a bit potty. Yeah, negative 59. The key thing about that is that it is a negative, right? It's negative 59. And therefore, we need to write something like, since the discriminant is negative, there are no real roots or no real solutions. Okay, so no real roots. And I'm just going to check the mark scheme, see if they require anything else. Yeah, that's it. So you show negative 59 and the conclusion no real roots will gain you the marks. Okay. All right, then part B, we want to solve this equation here. Now this is basically a clear hidden quadratic, and the best way to see that is to use a substitution. So we're going to say let u equal the cube root of x, and if we do that, that means we're going to get 12 upon u minus u is equal to 4. We multiply everything through by u, so we get 12 minus u squared. Beg your pardon, sorry about that. U squared is equal to 4u, which means that 0 is equal to u squared plus 4u minus 12. And we can factorize that. So I think that will give us u plus 6 and u minus 2. And the reason for that is we're looking for two numbers that multiply together to give negative 12 and that add up to give positive 4. And positive 6 and negative 2 do that. Okay, so that means we've got solutions u is equal to negative 6 and u is equal to positive 2. But of course, we said at the beginning that u is the cube root of x, right? So the cube root of x is equal to negative 6 and the cube root of x is equal to 2. So what we've got to do is we've got to cube both sides of these, right? So if I cube negative 6, I think I'm going to get negative 216. So let me just do that. So turn on my calculator. 6 to the power of 3. Yeah, 216. That's negative 216. And if I cube 2, I'll get 8. So my two answers that I think I get are negative 216 and 8. And I will just check the mark scheme, make sure that I'm right about that. So let's go down. Yep, those are the two correct answers. Okay. Okay, so here we are in question 4, which is a factor theorem, remainder theorem style of question. So we really need to know what those two theorems are. So I've started by writing out the remainder theorem for you here in blue. The remainder theorem basically states that if we divide a polynomial by x minus a and we get a remainder of r, then it means that if we substitute a into the polynomial, in other words, if we find p of a, then we will get that remainder r, right? So if I divide a polynomial by x minus a and get remainder r, then p of a is equal to r. It's best illustrated with an example. Let's say I took a polynomial and divided it by x minus 3, and I get a remainder of 7. Then what that means is if I was to substitute 3 into the polynomial, I would get 7, right? Or another example, if I was to divide my polynomial by x minus 10, and get a remainder of 4, then what that means is if I was to substitute 10 into the polynomial, I would get 4. So in this particular case, we want to find the remainder when p of x is divided by x minus 2. Well, we could do a polynomial division, but that'd be kind of crazy, right? Because it's only worth 1 mark. It's not worth all that work. So instead what we say is, okay, if we were to substitute 2 into the polynomial, then what we would get is we get our remainder. So we're going to exploit the remainder theorem here because it makes our life easier. So we're going to find P of 2. And that means we're going to get 6 times by 2 cubed. 2 cubed is 8, plus 2 squared is 4, minus 12 times by 2, which is 24, plus 5. And 6 times by 8 is 48, plus 4 minus 24 plus 5. Okay, now 48 minus 24 is 24, and 24 plus 4 is 28, and 28 plus 5 is 33, and 33 is our answer. Okay, so that's part A, that's worth 1 mark. Part B, we want to show that 2x minus 1 is a factor of P of x. Well, okay, this is using the factor theorem. Now, factor theorem is actually basically a consequence of the remainder theorem, if you really think about it, but I'll write it out here nice and simply for you. If x minus a is a factor of a polynomial, then x equals a is a root, right? So if x minus 5 is a factor, 5 is a root. If x minus 12 is a factor, then 12 is a root. If x plus 8 is a factor, then minus 8 is a root. Because if you think about it, it's x minus minus 8. It's the same thing as x plus 8. Okay, and we should probably just state what a root is for those of you who are not sure, right? If f of a is equal to 0, then a is a root of the polynomial f of x, right? So in other words, a root is an x-intercept. It's the value where the function is equal to 0, right? So if 3 is a root, it means if we would substitute 3 into polynomial, we will get 0. If 5 is a root, it means if we substitute 5 into polynomial, we'll get 0, which is actually the same thing as the remainder theorem, right? Right? Because what we're saying is we get a remainder of 0, right? So there's no remainder when we've got a root. Therefore, what does that mean? It means that if we were to divide by x minus a, then it must be a factor, right? So if a is a root, it means that we've got a remainder of 0, which means that x minus a divides through by the polynomial such that there is no remainder, which is the same thing as saying that, that x minus a is a factor. Okay, so let's have a look at part B here. I want to show that 2x minus 1 is a factor of P of x. Well, okay, if 2x minus 1 is a factor, that's actually the same thing as saying x minus a half is a factor, right? So I pull out the 2. And so if x minus a half is a factor, then it means, therefore, that we should expect x is equal to a half to be a root of the polynomial. And how can I show that x equals a half is a root? Well, I just got to substitute it in, right? I've got to find p of a half. So let me find out what the function was. It was 6x cubed plus x squared. Okay, so we got 6 times by a half cubed, which is an eighth, plus a half squared, which is a quarter, minus 12 times by a half. So that's going to be minus 6, isn't it? Plus 5. Well, 6 upon 8 is 3/4. 3/4 plus a quarter is 1. So we've got 1 minus 6 plus 5, and that's equal to 0. So we can write a statement like, since x equals a half is a root of the polynomial, then x minus a half is a factor. And of course, if x minus a half is a factor, it's actually the same thing as saying that 2x minus 1 is also a factor, right? Those two statements are equivalent. Okay? All right. Part 2, hence write P of x as a product of linear factors. All right, well, basically, what we've just shown is that if we've got P of x and we divide it by 2x minus 1, right? 2x minus 1 is a factor. That means that if we were to do the division, we will get some other factor, a quadratic factor as a result, with no remainder, right? With 0 remainder there, okay? So what we're going to do is just going to do a polynomial division, basically. So if I do the polynomial division, so 6x cubed, so let me just get rid of that, 6x cubed plus x squared minus 12x plus 5. I'm going to just make sure that I've got that right. Okay, And then we're dividing this all through by 2x minus 1. Okay, so we're going to take the leading term, 6x cubed, divided by 2x. We get 3x squared. 3x squared. We're going to take the 3x squared times it by 2x minus 1. 6x cubed minus 3x squared. Okay, and then we're going to subtract, okay, the bottom from the top. So 6x cubed minus 6x cubed is 0. X squared minus 3x squared is plus 4x squared minus 12x plus 5. So 4x squared becomes the new leading term. So I do 4x squared divided by 2x, which is going to give me positive 2x. I'm going to take that 2x and multiply it by my entire divisor here. And so that's going to give me 4x squared minus 2x. And I'm going to subtract that off. So 4x squared minus 4x squared is 0. Negative 12x minus 2x is plus 2x. So that gives me minus 10x plus 5. Negative 10x becomes the new leading term. I divide it through by 2x, which is going to give me negative 5. And so if I take negative 5 and multiply through, I get negative 10x plus 5. And of course, if I subtract that off, I get 0 as I expect. Okay, so what have we shown? We have shown, therefore, that p of x can be written as 2x minus 1 times by 3x squared plus 2x minus 5. So 3x squared plus 2x minus 5. I just want to double check that. Yeah. And we were asked to write this as the product of linear factors, I think, which implies that that quadratic will factorize. So we've got 2x minus 1 bracket 3x and a 3x. Oh, sorry, not a 3x and a 3x. Sorry, a 3x and an x. And we want to choose two numbers that multiply to give negative 5. Well, it's either going to be positive 1 and negative 5 or the other way around, right? Negative 5 and positive 1. So I think that that would have to be a positive 5 here and a negative 1 there. The reason for that is if I was to multiply through, 5 times by x is 5x. 3x times by negative 1 is negative 3x. So 5x minus 3x is 2x. So that works out. Okay. So what else are we required to show? No, that's it. We've written it as the product of linear factors. Okay, so I think we just got one last part. Hence, solve the equation 6 sine cubed theta is equal to, plus sine squared, blah, blah, blah. Okay, basically, if we do the substitution x is equal to sine theta, sorry, beg your pardon. If x is equal to sine theta, then this just gives us the polynomial that we had before. Okay, so it's recognizing that this question, part 3, is connected to what goes before. And the key to that, of course, is the word hence. And we've just found out that we can write this polynomial as 2x minus 1 times by 3x plus 5 times by x minus 1, I think. Yep. And so therefore, this has got solutions of 2x minus 1 is equal to 0, which means that x is equal to a half, or x is equal to negative 5.3, or x is equal to 1. And so therefore, sine theta is equal to a half, or sine theta is equal to negative 5.3, or sine theta is equal to 1. Now, immediately we should recognize that the middle of these is not possible, right? Because negative 5.3 is a value that is not within the range of positive 1 and negative 1, right? So that guy's out. There are no solutions there. But then we want to find the other solutions. We want to do it between 0 and 90 degrees. Okay, well, I know you guys, many of you will probably hate me for this. You hate graphs, right? Well, I just think graphs are by far the easiest way to do it. I'm really sorry. I'm going to keep telling you to do that. So this is the sine wave, right, between 0 and 180. I'll just draw the full thing. There you go, like that. All right, so that's the sine graph, 180, right, 90 degrees there. Okay, so basically we just want to find solutions in this first part. So if sine theta is equal to half, that is going to give you theta is equal to 30 degrees on your calculator. We don't need to have any other solutions because that's just that one there. And if sine theta is equal to 1, well, that's going to be theta is equal to 90 degrees. and that will be the only solution there. Let me just double check. It was less than or equal to 90. Yeah, it's less than or equal to 90. So I think we've just got two solutions there, 30 and 90 degrees. And I'm going to check the mark scheme just to make sure that that's correct. 30, 90. And you need to state that there's no value from sine theta is equal to negative 5.3. Okay, which I did by crossing it out. Okay. All right, then, question 5. A curve has this equation here. The tangent to the curve at the point where x equals 1 cuts the x-axis at the point P. Find the equation of the tangent in the form y equals mx plus c, and hence find the x-coordinate of P. Okay, so we want to find the tangent to the curve. Okay, what do we need to find the equation of any line? We need two things. We need the coordinate point on the line, and we also need the gradient of the line. Okay, so how are we going to get those two things? Well, we know the x-coordinate is where x is equal to 1. How do we get the y-coordinate? Well, we substitute into here. So we're going to state when x is equal to 1, y is equal to 5e to the 2 times by 1, which is 2 minus 1, so that's e to the 1, plus e to the power of 1. And so that's going to give us 6e to the power of 1, or just 6e. So we got the coordinate point. It is the point 1, 6e. And then we want to find the gradient. Well, how do we find the gradient? We just need to differentiate. Okay, so if y is equal to 5e to the power of 2x minus 1 plus e. Just check I got that right. Yeah. Then we want to differentiate this. So y prime, how do we differentiate the exponential? Well, the exponential remains the same. So we get 2x minus 1. But we need to differentiate the power. If we differentiate 2x minus 1, we get 2. So we need to multiply through by 2. So 5 times by 2 is 10. Right? So what's happened here is we've got a chain rule, basically. Right? The function e remains the same. But the function that's inside it, the 2x minus 1, we need to differentiate and multiply through. Lastly, if we differentiate e, e is just a constant, so it differentiates to give 0. Okay, so that's the derivative. So now we're going to substitute in when x is 1. So when x is equal to 1, y prime will equal to 10e to the power of 2 times by 1, which is 2, minus 1 is 1, so we get 10e to the 1 is the gradient. So we've got a gradient of the tangent is 10e. Okay, so how are we going to get the equation of the line? Well, we use the form y minus y1 is equal to mx minus x1. So our y1 value was, what was it? 6e. So we get y minus 6e is equal to 10e bracket x minus 1. So if I was to expand this, I get y minus 6e is equal to 10e times by x minus 10e. And if I add 6e to both sides, I get y is equal to 10e times by x minus 4e. Okay, so I think that's got it in the form y equals mx plus c. So our m there is 10e and our c is negative 4e. And what else we asked to find? Yeah, I've done that. Hence find the x-coordinate of P. Well, what is P? It's where it cuts the x-axis. All right, so we just say x-intercept. X-axis intercept is when y is equal to 0. So we're trying to solve 0 is equal to 10e x minus 4e, which is the same thing as solving 10e x is equal to 4e. So we divide through, so we get 4e divided by 10e, so the e's cancel off. So we get 4 upon 10, which is 0.4, or is 2/5 as a fraction. Okay, so x is equal to 2/5 should be the answer. Let me just scroll up, make sure I've done everything. Yeah, find the x-coordinate P. I think it's 2/5. I'm going to check that against the mark scheme. Yeah, 0.4 or equivalent. Okay. Okay, then, question 6, which is a trigonometric question. We want to show that sine cubed x times by cosec x over cot x can be written as sine squared tan x. So we basically got an identity question. We want to show that this thing can be rewritten as that. Now, if you've seen me do these questions before, basically what I try to do is I try to change everything immediately into sines and causes. It's not always the best way, but I would say 9 times out of 10, it is the best way. So I'm going to change everything in here into either a sine or a cos. Okay. The other thing I do is, because I just find it visually easier, I use a substitution. I say let s equal sine x and let c equal cos x. So I just think it makes it easier to work through the algebra, to be honest. Okay, so sine cubed x I can write as s cubed. Now cosec x. Now what is cosec? It's 1 divided by sine. How do I know that? I look at the third letter. 1, 2, 3, right? The third letter of cosec is s. So cosec is 1 divided by sine, okay? And then cot, what's the third letter? 1, 2, 3, t. So cot is 1 divided by tan. Now, we know from the basic identities that tan theta is equal to sine theta over cos theta. So if we were to flip that, if we were to invert it, 1 upon tan is cos upon sine, right? So if tan is sine upon cos, 1 upon tan will be, the flip of that will be cos over sine. So I can write here cos divided by sine. Okay, all right then. Now, I just want to try to simplify this and to tidy it up. The thing that's causing me the difficulty is kind of this fraction here, because we've got fractions within fractions. So what can I do with that? Well, I'm going to get rid of the signs that are on the denominator. And the way I'm going to do that is I'm going to multiply the top and bottom by sine. So if I do that, so I've got my s cubed still, then on the numerator I've got 1 upon sine times by sine, which is just equal to 1. And I've got cos upon sine times by sine, which is just going to give me cos. So I've got sine cubed divided by cos. Now, what am I aiming for? I am aiming for sine squared tan x. Well, we already know that tan is sine divided by cos. So basically, I want to have a sine here, don't I? So I can divide it through by that cos. So I'm going to split up my sine cubed into sine squared times by sine and divided by cos. And I can say, all right, well then I've got my sine divided by cos, which is equal to the tan. So this becomes sine squared x times by tan x. Okay, and that's our answer. Okay, next part, we want to solve this equation here for x is between negative pi and pi. Well, look, we don't have the word hence, right? So hence usually means we've got to use the previous identity in part A. We don't have that, so we can treat it as a separate question. I think it's a bit tricky, but we've got a tan x here, and we've got a tan x here, so I think we can just factorize. So if I was to factorize out tan x, I'm going to get tan x, big bracket, cos squared x minus a half, okay, is equal to 0. So I've just factorized that, which means I've got 2 solutions, right? Because I've got 2 things multiplied together that give me 0. I either got this thing here, will be equal to 0, or this thing here will be equal to 0. So let's write that down. Either tan x is equal to 0, or we've got cos squared x minus a half is equal to 0. Well, let's take the cos squared. We're going to get cos squared x is equal to positive a half, right? And therefore, cos x will be equal to plus or minus 1 upon the square root of 2, okay, or root 2 upon 2, right? So we need to remember the plus or minus here. Now, if we're going to solve these 2 things and we want to solve them between negative pi and positive pi, there are a couple of ways that, that we could do that. One is to use graphs, one is to use the unit circle. And I think what I'll do is I'll do a little bit of both just so that you can see. So I'll solve the tan x, I think, with the graph, and I'll try to solve cos x with the unit circle. Okay, so let's go down. We try to solve tan x is equal to 0. Well, let's draw out the tan graph. Ooh. What does the tan graph look like? Looks something like this. And the key thing about the tan graph is it has got asymptotes at 90 degrees and minus 90, or rather pi by 2 and negative pi by 2. So we're going to have an asymptote there. Okay, and going to have an asymptote there. Okay, pi by 2 and negative pi by 2. Okay, and then that would be pi by 2, negative pi by 2, negative pi. And then we'd also have another asymptote at 3 pi by 2, right, like that. And at negative 3 pi by 2. Now, what does the tan graph look like? Tan graph looks like this. Like that. Like that. Ooh, and it will repeat. Like that. Ooh, it's not very good. Try that again. Never mind. Like that. And like that. Oh dear, it's even worse. Never mind. It's all right. Okay. Like that. Now, when is tan x equal to 0? Well, it's equal to 0 everywhere on the x-axis, isn't it? So it's going to be equal to 0 at 3 points that I can see. It's either going to be 0 here, or here, or here. And of course, if you just use the calculator, all you're going to get is you're going to get x is equal to 0. You're going to miss out the two other values of negative pi and pi. But let's just check that. Ah, well, here, if they wanted to be mean, right, they could make this greater than or equal to negative pi and less than or equal to pi. But because they don't have the equal sign, actually these two values are excluded. Okay, and so we're just left with x is equal to 0. So I suppose in this case, you probably don't need to use the graph, but as I said, I think it's better that you do understand how it works. And if they did want to be a bit harsh, right, which they could do in a future paper, then they could test students to see whether or not they got this value here at pi and this value here at negative pi, right? That would be a great question, actually, I think. Okay, cos x is equal to plus or minus 1 upon root 2. Well, let's try to do that. So cos x is equal to plus or minus 1 upon root 2. And of course, you could use a calculator for that, couldn't you? Let me just get my calculator set up. So cos inverse of 1 over root 2. Ooh, boink, boink. And that gives me pi by 4, right? Because it's one of those critical angles. So you get pi by 4. Okay, well, if you were to do negative 1 upon root 2, so negative 1 divided by root 2, okay, and you do the cos inverse of that, then what would you get? You get 3 pi by 4, but that's not within the set of values that we want, right? Because we want between pi and negative pi. Okay, well, let me do a unit circle, so at least you can understand the principle of this idea. And of course, you may not choose to use it in an exam, but I think it's helpful for you to know. Now, here we got a unit circle. What is a unit circle? A unit circle is the circle with radius of 1. Okay, so this circle here has got radius of 1. Like that. And basically, you imagine you got a point and it's moving all the way around the unit circle, right? So you're moving this point all the way around the unit circle such that the point is making an angle theta with the positive x-axis, right? So this would be like whatever, 20 degrees, 50 degrees, 90 degrees, right? And so on and so on and so on. Now, as you go around the unit circle, what you're finding is for each value of theta, you're going to have a different x-coordinate and a different y-coordinate, right? So here, when theta is 0, your x-coordinate is 1 and your y-coordinate is 0. Here, where theta is 90 degrees, your x-coordinate is 0 and your y-coordinate is 1. Here, when you go to 180, your x-coordinate is -1 and your y-coordinate is 0. Now, what's the significance of this? Basically, what we call cos theta is the same thing as the x-coordinate on the unit circle, right? So for example, here again I said, when theta is 0, our x-coordinate is 1. Well, yeah, cos 0 is 1, right? What about if we take theta is 90 degrees, right? When theta is 90 degrees, the x-coordinate is 0. Well, yeah, because cos 90 is 0, right? So basically, when we're using cosine, what we really mean is, for that particular angle, what is the x-coordinate on this circle? And the same thing is true with sine, right? Sine theta, what do we mean by that? We mean the y coordinate, right? So sine is telling us for every single value of theta, what is the y coordinate on this circle? Yeah, so the y coordinate is given by sine theta. Sorry, I got interrupted in the recording. So for any value of theta, let's say theta is 0, then what's the y coordinate? The y coordinate is 0, and that should make sense because sine 0 is 0. If theta is 90 degrees, what's my y coordinate? My y coordinate is 1. And yeah, because sine 90 is 1. So basically, cos theta tells you the x coordinate on the unit circle. Sine theta tells you the y coordinate on the unit circle. Now, we're not interested in sine at this point in this question, so I'm going to get rid of that. I'm going to get rid of that there. We're just interested in solving cos theta is equal to plus or minus 1 upon root 2. Well, if we want to solve where cos theta is equal to plus or minus 1 upon root 2, what we're really saying is, what are the angles where the x coordinate is plus or minus 1 upon root 2, right? So what I'm going to do is I'm going to draw this line here, right? That's the line. X is equal to positive 1 upon root 2. And this is the line here. X is equal to negative 1 upon root 2. Probably drawn those quite badly, actually, but never mind. Yeah, let me undo those. So I want to make it a tiny bit better. Go undo. Make it like there. Yeah, it's a bit better. And over here. Ooh. Yeah, something like that. Okay, so this is x is equal to positive 1 upon root 2. This is x is equal to negative 1 upon root 2. And so basically what we're trying to do is we're trying to find the angles at this point, this point, this point, and this point. Okay? Well, if we do that, that angle there is 45 degrees. Okay, so that angle there is 45 degrees. Or pi by 4 radians, beg your pardon. Okay? And this one here, what will that be? Well, actually, if we just use symmetry, right, this angle here is also going to be pi by 4, right? Because if that's pi by 4, then that's pi by 4. So this angle here will be 3 pi by 4. Okay, so we're going to have theta is equal to pi by 4, 3 pi by 4. What about this angle down to here? Ooh, beg your pardon. This angle there. Well, that is going to be negative pi by 4, isn't it? Because I'm going down, right? And by symmetry, that angle there will be the same as that angle there. So we've got negative pi by 4. And again, by symmetry, this guy, this angle, will be negative 3 pi by 4, right? So if that angle was 3 pi by 4, that one there, by symmetry, this one will be negative 3 pi by 4. So we've got that and negative 3 pi by 4. Okay, so I think those are going to be all my solutions. So total solutions will be x is equal to negative 3 pi by 4, negative pi by 4, 0, because that was the solution for the tan, pi by 4, and 3 pi by 4. Okay, I think those are all the answers. Now I'm just going to check the mark scheme, see if that's what they've got. Let's go down. Tan is 0, yeah. Plus or minus pi by 4, plus or minus 3 pi by 4. Okay, so that's a complete answer here. I really hope that going through both methods, right, the understanding the unit circle and also going through a graph helps you to see that there are different ways of doing these questions. I know the way I'm doing it it requires a bit of work, right? And it's a bit long-winded, and you say, oh, it's unnecessary, right? The calculator just tells me the simple answers. But the problem with that is they construct the questions in such a way that the calculator is not always going to give you the answer that they're actually looking for, right? You are going to have to understand how sine, cos, and tan actually work, and that's going to require you either knowing the graphs or understanding where sine and cos come from, which is ultimately the unit circle. Okay, so I'd encourage you as much as you can, as with all ad maths, right? You want to try to understand what's going on underneath so that you can explain it adequately to yourself, so that you can answer questions confidently because you really know what's going on. Okay, so I hope that was helpful. Sorry that it took me a while to get through it. Okay, question 7, which is a combinations permutations style of question. Find the number of different ways the 9 letters of the word polymaths can be arranged when the O and the A are not next to each other, right? The key word there is not. Now, I think probably the easiest way to do this is to consider the number of ways in which they are next to each other and subtract that from the number of ways in total that you can arrange polymaths. Okay, so the number of ways without any restriction, right? So in other words, you can just do whatever you want. The O's and the A's can be next to each other, or they can't be, doesn't matter. Well, how many letters in polymaths have you got? You got 1, 2, 3, 4, plus 5 is 9. So that's 9 factorial, or if you prefer 9p9, right? 9p9 because you've got 9 items, you're arranging 9 of them, and the order matters, okay? And then what's the number of ways if the O and the A are next to each other? Well, let's just think about that. We've got 9 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what we're going to do is we're going to group up the O and the A. So let's kind of consider them like that. That's 1 unit there. So then how many units do I have to arrange? I've got 1, 2. I'm going to consider this thing as one thing, right? So that's 3, 4, 5, 6, 7, 8. So I've got 8 items to rearrange, but then inside this O and A, the number of ways I can rearrange those are going to be 2 factorial, right? So I can rearrange the O and the A 2 times. So the number of ways if OA together is going to be equal to the 8 factorial, because that's the number of ways I can like arrange the big items, the 1, 2, 3, 4, 5, 6, 7, 8 items, times by 2 factorial. Because right, for each one of those 8 factorial ways of arranging all the big items, there's a further 2 ways of arranging O and A, right? So let's say, you know, the big item was here. I could either have O here and A there, or the other way around, A and O in the opposite order. Okay? So then the number of ways if not together is going to be equal to 9 factorial minus 8 factorial times by 2 factorial. Okay, and we should probably try to figure out what that is. I'm just going to use a calculator because I'm a tiny bit lazy. 9 factorial minus 8 factorial times by 2. And I get 282,240, 282,240. Just very quickly check the mark scheme, make sure that that's right before I carry on. 282,240 is the right answer. Okay, well, let's move on to the next one. B, the letters maths are together and in this order, right? That's a key thing, right? You want to be very careful that you don't skip that out, okay? So let's consider it in exactly the same way. How many letters we got? We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's group together the maths. So we've got maths there like that. But now in this particular case, we actually know that maths must be written as M-A-T-H-S. In other words, we can't rearrange these letters inside their big grouping. Okay, so how many ways can we do this? So a number of ways. Well, let's count the number of items. We've got 1 item here, 1 letter, 2, 3. This whole thing counts as 1 item now, so that's 4, 5, right? So we've got 1, 2, 3, 1 whole item, 4, 5. So how many ways can we arrange it? 5 factorial. And 5 factorial, I think, is 120. Let me just put in the calculator, just make sure. 5 factorial, 120. Okay, so I think the answer to that is 120. Let me just double check the mark scheme again. Yeah, 120 is the right answer. Now, guys, this is going to cause a lot of people to slip up and make a fail, because what they're going to do is they're going to do 5 factorial times by 5 factorial for the maths, okay? And they're going to do that for 1 or 2 reasons. First reason is they haven't read the question properly. They have assumed that the question is the same as all the other past papers, and so, you know, you got a bit careless, you haven't read the question. that's group one. Group two is they've read the question, but basically the way they've learned permutations and combinations is they've categorized the questions into different groups. And they said, for this type of question, I do this. For this type of question, I do that. For this type of question, I do the other. And actually, they've got no real understanding of why they're doing that, right? So they're going to look at this and go, okay, yeah, 5 big items, 5 factorial, and 5 letters inside here times by 5 factorial again. And, you know, I just do that just because that's the steps law. That's what we do. But what that's revealing is actually you don't really understand what's going on, right? And that's always the biggest problem in maths and add maths. You need to try to understand what's going on. Why is it that we usually multiply by the 5 factorial? Well, because what we're saying is, for each of the ways we can arrange the big items, by big items I mean these, 1, 2, 3, 4, 5 items. Inside here, we can also rearrange these letters in most of the other questions. And then how many ways can we rearrange those letters will be the number of letters 1, 2, 3, 4, 5, and we times by 5 factorial, right? Because in other words, for each way that I could rearrange the big items, there is a further 5 factorial ways of arranging those little items on the inside, okay? So that's the reason we're multiplying in that case. But of course, in this particular question, we're not asked to rearrange these letters. And so for how many ways can we rearrange maths in that block? Well, there's only one, right? Because it's got to be maths. Okay, so I know that I may be sounding a little bit annoying. I do apologize for that. But with all these things, right, you want to try to understand what's actually happening in each question, why you're doing what you're doing. The more you can understand it, then actually these kind of questions are not going to trip you up. All right, so that'd be my suggestion. Because obviously I hope that you'll be able to be very successful in all of these. Okay, take care. Okay, question 8. An experiment was carried out and the values of y for certain values of x were recorded. The table shows the values, so that's there. The relationship between x and y is modeled on this equation, a e to the kx. Draw a straight line graph for ln x against ln y, beg your pardon, against x. Well, that should be fairly straightforward. They actually tell you what to do, right? Ln y against x. So we just got to find ln y, right? So let's do that. Get our calculators out. So we need to do ln 10, 2.30. To be honest, 1 decimal place is enough really for the graph. Ln 13. Sorry, beg your pardon. 2.56, so okay, 2.6. Ln 22. 3.03, so I just write 3.0. Ln 35, 3.55, okay, so 3.6. And then ln 50, ln 50, 3.31, so 3.3. Okay, so we need to plot this, and they very nicely, they haven't always done this, but they very nicely put the scale on, right? So, so let's do that. So we want to plot on the point 15, 2.3. So 15, 2.3. So let me put that on. 15, 2. Oh my goodness. 1, 2, 3. I think it's there. Oh. Yeah, sorry. It's kind of hard for me to tell on the screen. Do beg your pardon. And then we want 32.6. So 32.6. So 4, 5. I think that's 6 there. Right, like that. And then 45, 3. Well, that should be easy. So 45, 3. Okay. And 60, 3.6. So 60 is there. 1, 2, 3, 4, 5, 6. I think that's there. Okay. And 75. 3.3, that can't be right, can it? I must have made a mistake. Ln 50. Wait a second. Oh, 3.91. Sorry, I misread my calculator. I do apologize. Let me just change that. 3.9. Okay, so I need to plot that on 75. That. All right, there we go. So we've got a straight line graph. Now we just need to draw a straight line that goes through it. So let's see if I kind of start roughly there. I think that's probably fair enough. Yeah, so that'll keep that as my straight line graph. All right. Find the equation of the line in part A and hence find the values of A and K. Give each value correct to one significant figure. All right, well, I'm going to go back to this equation here. Y is equal to AE to the KX, right? So Y is equal to AE to the KX. So I always start with this. And then what I'm going to do is I'm going to take the natural log of both sides. So I'm going to find ln Y is equal to ln AE to the KX. Okay, I can use the log rules and split this up. I got ln A plus ln E to the KX, right? Because log A times B is equal to log A plus log B. And then I can use the log rules again, and I can bring the power of kx down, or actually I can just say, because log is log base e, this thing here is just going to be kx, right? So I'll do it the long way just to make sure that you're happy with it. This is ln a plus kx times by ln e, but ln e is just equal to 1, so that guy kind of disappears. So what have we got? If I was to rearrange this, we have got ln y is equal to kx plus ln a. Okay, now this is a straight line graph, because if I was to plot ln y as my y and x just keep the same, right, as x, then what's the k here? The k is going to be my gradient m, and ln a is going to be my y-intercept c. Okay, so we got a straight line graph if we were to plot x against ln y, right? Which is what we got on the previous page. And so if we want to find k, what do we need to do? We just find the gradient, because the gradient's equal to k. And how do we find a? Well, we know that ln a will be equal to the y-intercept c, right? So basically, we just got to find the gradient. Well, I think to find the gradient, to be honest, probably the easiest thing is to just use two extreme points. So I'll use this point here and this point, this point here, beg your pardon. So the gradient m is equal to y2 minus y1. So I think it was 3.9 minus, what was it, 2.3? 2.3 over x2 minus x1. So 75 minus 15. And if I was to do that, so 3.9 minus 2.3 is 1.6. 75 minus 15 is 60. So 1.6 divided by 60, 1.6 divided by 60. 2 upon 75, 0.0266 recurring, 0.02627. I'm just going to quickly check the mark scheme to see if they get a value that's similar to that. So where are we? Okay, they will accept 0.02 or 0.03, right? So actually they've got quite a good, good tolerance there. So I said before that the k value is equal to the gradient, so I'll say k is equal to 0.03. Okay, all right then. What else did I say? I said that the y-intercept is going to be equal to ln a. So what's that y-intercept there? That looks like 1.8. So I'm going to say my y-intercept is equal to 1.8. And therefore ln a is equal to 1.8. And so if I want to find a will be equal to e to the power of 1.8. So let's stick that into the calculator. I've got e to the power of 1.8. And I get 6.049. So I guess probably can say 6. And again, I'm just going to check the mark scheme, see what they accept. They accept either 6 or 7. Okay, so A is equal to 6. Okay, Is there any other part of this that I need to do? Okay, part C, find the value of x for which y is equal to 17. We could probably use our graph, I guess. So let's go back to the graph. If y is equal to 17, what's ln y? Ln 17 is equal to 2, I'll make sure I read my calculator probably, 2.83. So that's going to be kind of roughly here, right? 2.83. So we'll call that ln 17. So if we draw a straight line across, right, we can do that. And then we can read it straight down. And we get an x value there. And that x value is halfway between the 30 and the 45, isn't it? Right? So 30 plus 45 divided by 2, I get as 37.5, something like that. And again, I'll just check the mark scheme, see if they got a value in that kind of ballpark. Yeah, they accept anything from 33 to 37.5. So actually, I was just on the edge, okay. And you get the mark just for having the right value. So probably, you know, because I'm doing it on the screen, it's a little bit hard to get it exactly right. But if you get something, you know, 37.5 would have been accepted, but it's kind of just close to the boundary. Now, another way of doing it instead of using the graphical method is you could substitute in, right? You've already, let's just go across to here, right? We could say, okay, ln 17 is equal to kx, and k we said was 0.03, yeah? So 0.03x plus ln a, and I had ln a, our c value was 1.8, I think. So I could rearrange this. I would do ln 17 minus 1.8 equals, and then divide that by 0.03, and I get x is 34.4. So actually I think that's better, isn't it? That's closer to the range of acceptability. So probably a good thing for you to do, right, is you do both methods. You do the graphical method and you also substitute in the equation, and you got two values. You will have to choose one, by the way. You can't submit two answers. But I would think, you know, I would probably incline to use the equation because I think the graphical method tends to be a bit rough. But hopefully the two should be kind of close to each other. So you sort of get a rough a way of confirming your answer, basically. All right. I hope that was helpful. Okay, question 9. The diagram shows part of the curve 32x minus 4x squared minus 48 and the line AB. The curve and the line AB meet the x-axis at the point A and meet again at the point 512, which is the point B. The line CD extended is parallel to the y-axis, or in case it's a vertical line, basically. And passes through the maximum point of the curve. Okay, so I'm just going to indicate that on my diagram, right? That point there is the maximum point. Okay, and we want to find the area of the shaded region. So we want to find this area here. Okay, so let's break down a big problem into lots of smaller problems. If we want to find this area here, right, that area there, then what's it equivalent to? It is equivalent to finding the area underneath the curve between A and C, right, between A and C, and subtracting away from it the area of that triangle, right? That's how I would do it, okay? So you take the area of the curve between A and C by integration, and then you subtract away the area of the triangle. Now, in order to do that, what would I need to know? If I want to integrate this curve between A and C, I'm going to need to know the coordinates of A and the coordinates of C, right? So I need a way of finding out what A and C are. And if I was to find the area of the triangle, then not only do I need to know A and I need to know C, but I'm also going to need to know the coordinate of D, right? So let's try to break that down. Let's say that first of all, what I want to do is want to find the coordinate of A. Well, A is the x-intercept of this curve here. Okay, so I'm going to find the x-intercept of the curve. So I'm going to write down here x-intercept x-intercept is when y is equal to 0. So I'm trying to solve 0 is equal to, I'm going to write it out as a proper quadratic, right? Negative 4x squared plus 32x minus 48. And that thing is begging to be divided by negative 4. So I'm going to get x squared minus 8x plus 12. And I think that should factorize quite nicely to give bracket x and x. And I want two numbers that multiply together to give positive 12, but add up to give negative 8. That's going to be negative 2 and negative 6, isn't it, right? Those are going to be the two numbers. And so that means we've got x-intercepts when x is equal to 2 or x is equal to positive 6. Well, if we go to our graph, right, obviously what's going to happen is A is going to be the coordinate where x is 2. And why have we got 6? Well, because if we imagined extending down that quadratic like that, 6 is going to be this point. Okay, that's going to be the other intercept, which also means that we can basically figure out what the maximum point is, right? Because the maximum point is the vertex of this quadratic, and the vertex is always in between the two roots or the two x-intercepts. So what's the midpoint of 2 and 6? Well, it's going to be 4, isn't it, right? So we pretty much know that the x-coordinate of C is also going to be 4. Okay, all right then. So we now know our A and we know our C. So we're going to be able to integrate underneath the curve between those two values. But we said that what we need to do is we also need to find out what the point D was, right? And D is the intersection of this unknown line AB and the vertical line x is equal to 4. So firstly, it'd be good to find out what the line AB is, right? So how are we going to find the line AB? We could find the gradient and then substitute into y minus y1 is equal to mx minus x1, right? So let me go over to the left, I think. Okay, I'll go over here because I still want to be able to see the graph. I want you to see it as well. So the gradient of the line AB is equal to y2 minus y1. So we've got 12 minus 0 over x2 minus x1. So 5 minus 2. So we've got 12 divided by 3. So that thing there is equal to 4. And we can substitute in y minus y1. So y minus 12 is equal to m, which is 4, x minus x1, which is 5. So I'm using the point B there. And if I was to simplify this, I get y minus 12 is equal to 4x minus 20. So y is equal to 4x. I'm going to add 12 to both sides, so 4x minus 8. Okay, so that line there, the line AD, right, this guy, right, that is the line. Y is equal to 4x minus 8. 4x minus 8. So how are we going to get to point D? Well, the point D is the intersection of that line with the line x is equal to 4. So we just substitute x is equal to 4 into our into the equation of line. So when x is equal to 4, y is going to equal to 4 times by 4, which is 16, minus 8, which is just equal to 8. Right? So D has got a y coordinate of 8. So I'm gonna take that there. Okay, so we've got the y coordinate of that is 8. All right, then. Well, I think we've got everything that we require in order to find the area of the shape. So the first thing I think I'll do is I'm going to find the area of the triangle because that's easy. So area of the triangle ACD is equal to a half of the base times by the height. Well, the base is this distance here, which is 4 minus 2, which is 2. And what's the height? Well, the height is this distance here, which is 8. Okay, so that thing there is 8. So 2 times by 8 is 16, divided by 2 is 8. So the area of the triangle is 8, so that's all very easy. So now the last thing I've got to do is I want to find the area that is underneath this curve, right? So the area basically of this entire region here, right? And I'm going to find that by integration. So area under the curve is equal to the integral of the curve, 32x minus 4x squared minus 48 dx between the bounds of 2 and 4. So now I just got to go through all of that integration. So if I integrate 32x, I get 32x squared divided by 2 minus 4x cubed divided by 3 minus 48x. And of course, 32 divided by 2 is the same thing as 16. So I'll just write that as 16. Okay, so now what I'm going to do is I'm going to substitute in the boundary of 2 and 4. And if I do that, I'm going to get a bit of a mess, aren't I? But never mind. I'm going to substitute in the upper boundary, which is 4. So 4 squared is 16. Times by 16 is 256. So 256 minus 4 cubed, which is 64, times by 4 is 256 upon 3. Minus 48 times by 4. So 48 times by 4 is 192. And I also need to substitute in x is equal to 2. So 2 squared is 4. 4 times by 16 is 64. And 2 cubed is 8. 8 times by 4 is 32. So I get 32 upon 3. And then minus 48 times by 2, which is 96. All right, so I'm very sorry. I'm just going to resort to a calculator. I'm going to add up all the bits that don't have thirds in them, right? So I'm going to get 256 minus 192, okay, minus 64, and then minus 96, which is plus 96. If I do that, I get 96. And now I've got negative 256, negative 256 thirds minus minus, so plus 32 thirds, which is negative 224. So now I've got negative 224 thirds. Okay, well, I'm going to convert the 96 into thirds. So 96 times by 3 is 288. So I get 288 thirds minus 224 thirds. So 288 minus 224 is 64. So I get there 64 thirds. And what is the area that I'm looking for? Well, it's going to be that 64 thirds minus the 8, isn't it? Right, for the area of the triangle. So the shaded is going to be equal to 64 thirds minus 8. So that's going to be 64 thirds minus 24 thirds, which is going to be 40 thirds. So the answer I get should be 40 thirds, and I'm going to check that against the mark scheme, and God willing, that should be right. So let me see. Mark scheme, where art thou? 40 upon 3. Lovely. Oh, wonderful. I'm so glad. Okay, now I hope one of the things you're learning as we go through questions like this is you're seeing how I do it. And one of the things I do is I break down problems, right? The reason why these things are hard is the integration is actually not very difficult. The thing that's hard is breaking down the problem. Now, there are a couple of issues with this. Now, the first thing is that when students look at problems, you instantaneously categorize them in your mind. And often what you say is, oh, I'm finding the area. This must be integration. And your mind immediately leaps to integration. Whereas actually integration is quite a small part of this question, and it's the part that happens right at the very end. So the better thing is say, okay, yeah, sure, I'm correct. I am going to have to use integration. I know that, but I'm going to just leave that to one side for a moment. The problem is really asking me to find this area here. Well, how can I do that? How can I break that problem up into smaller parts? Well, I can find the area under the curve, and then also the area of the triangle. All right, then what do I need in order to get those things? Well, I need to know the coordinate A and the coordinate C, and I need to find the equation of the line. All right, I need to do all this other stuff. Now, the moment you begin to work backwards and lay out your strategy of the things that you need, a big problem you'll find is actually composed of lots of little smaller problems. And so you know, one of the things you can do, which I think really helps, is you can write down in bullet points, this is what I need to find, right? I need to find this, I need to find this, I need to find this, and then just work through all of those problems. And if you do that, number one, you're going to be piling up the marks, right? Because there'll be a mark for finding the coordinate of A and C, the mark for finding the equation of the line, and all of that, right? So you're definitely going to be getting marks. You maybe get your 5 out of 9 marks, which is already great. But then also, you're clearing away the fog, right? You're beginning to see more and more information, which will enable you to actually get the end answer. So I hope one of the things I'm showing you is how to do problem solving. And a big part of doing problem solving is breaking down a big problem into smaller problems. Okay, guys, I hope that was really helpful. If you're liking these videos, please do like and subscribe and share with your friends. Okay, bye-bye. All right, here we are in question 10. The functions f and fg are defined like this. Explain why f inverse exists. Now, I got to say, I think that these particular questions, these functions questions, are among the hardest that appear on the paper. Students very often are coming to me asking me about these. Even though sometimes they're only worth 1 mark, they're challenging. Why are they challenging? Well, because they are very conceptual. You have to understand what's going on. And you have to be able to explain clearly, and explaining clearly and understanding are really the very difficult things to do. Now, I have recorded a long video where I've just gone through these types of questions because they've been very popular the last 3 or 4 years. And so I think it may be profitable to you to go through that video because I go into the nitty gritty and lots of detail. And I think you'd find that helpful. Okay, so I'm going to try to do this one a little bit quicker here. And essentially, the answer to this is understanding the distinction between one-to-one, many-to-one, and one-to-many mappings, right? So we've got one-to-one mapping. We've got many-to-one mappings. And we've got one-to-many. Now, these define the relationship between the number of inputs and the number of outputs, right? So one-to-one means we've got 1 input corresponds to 1 output. Many-to-one means we've got many inputs correspond to 1 output. And one-to-many means we've got 1 input gives you many outputs. Now, a classic example, let's say we had y is equal to 2x, right? That would be an example of a one-to-one function because for each input, 1 input, we've basically got 1 output, right? So if x is 1, y is 2. If x is 2, y is 4. If x is 3, y is 6, right? So each input corresponds to 1 and only 1 output, and that output could only have been achieved by that input, right? In other words, if y is 6, it must be the case that x was 3. There was only 1 input that achieved that. If we had instead the function y is equal to x squared, that would be many-to-one, because if we think about it, if we had the input x is 3, we would get an output of 9. But also if we had x is negative 3, we would also have the output of positive 9. In other words, there are 2 inputs, positive 3 and negative 3, that give us the same 1 output, which is 9, right? So if we've got many inputs that give us the same single output, that's many-to-one. And then lastly, if we were to have, for example, y is equal to the square root of x, okay, just thinking of it as a mapping, not as a function, then let's say that x was equal to 4, then y could equal to plus 2, or y could equal to negative 2. In other words, there's 1 input, 4, which has many possible outputs, namely 2 and negative 2. Now, for reasons that I'm not going to go into on this video, you can watch my long video if you want to know that, this guy here, the one-to-many, is not a function. Okay, one-to-many is not a function, basically because we don't want to have the situation where we've got many possible outputs to a function, all of which are equally plausible. Okay, we don't want that. So it's only one-to-one and many-to-ones, which are functions. Now, the second thing to understand is what happens when we invert a function. When we invert a function, we are reversing inputs and outputs, right? We're kind of flipping the order. So if we've got 1 input to 1 output, if we were to reverse that, if we were to invert it, then we would also have a 1-to-1, right? So if you think about it, if I invert the 1-to-1, f inverse, then I'll also get a 1-to-1. But if I was to invert a many to one, right, many inputs to one output, that will invert to give one input to many outputs, right? Because I'm flipping it. Well, hang on, I just said that a one to many is not a function. So this guy is not a function, right? That guy cannot be. So that doesn't exist. So what that means is that a many to one function cannot be inverted. So the only thing that we're left with is if a function is one to one, right, then it can be inverted, right? So if we've got a mapping that's one to many, it's not a function to start with, so it can't be. If a function is many to one, right, well, it is a function, but if we inverted it, we would get something that isn't a function. So what we're left with is only one-to-ones, because if we've got a one-to-one function, we invert it, we get another one-to-one, and that's totally fine. So basically, f of x, what is it? It is going to be a one-to-one mapping, right? So e to the power of x squared plus 3, where x is negative, basically is going to be one-to-one. So, and if you're not sure about that, by the way, it's because it will look something like this. Oh, shoot. Hang on. Graph will look something like that. Okay. So since this is one-to-one, you want to write something like, since f is 1-to-1, it can be inverted. All right. Okay, let me just check the mark scheme, see if they're requesting anything else in terms of what you need to write. Oh, it just says valid explanation using f. F is 1-to-1 or equivalent. Okay, yeah, so that should be good enough. Okay, part B, we want to find an expression for f inverse and state the domain and range of f inverse. All right, well, again, I've been through this in quite a lot of depth in the other video, but let me try to explain it. What is an inverse function? All right, here we got a function. Function takes inputs, which we usually call x, and gives out outputs, which are y. The job of the inverse function is to reverse inputs and outputs. So it'll take the output y as a new input, and it should give me back my original input x. Okay, so for example, if we were to put in x is equal to 2 into the function and get y is equal to 5, what that means is if we were to take 5 and put it into the inverse function, we should get back to 2. Okay, that's the job of the inverse function. Now, this has a corresponding implication for domain and range, right? Domain is the set of all the possible input values to a function. So here what we've got is we've got the domain of the original function of f, and the range is a set of all the output values. So this guy is going to be the range of f. Well, down here for the inverse function, what are we going to have? Well, this is going to be the set of the inputs for the inverse function, right? So the inputs is the domain of f inverse. Now, what do you notice? The set of all the values that could be put into the inverse function must be the same thing as the set of all the values that came out of the original function. And what that means is that the domain of the inverse function must be the same thing as the range of the original function, right? So whatever this is, got to be the same as that. In the same way, the outputs for the inverse function, which will be the range of the inverse function, has got to be the same thing as the domain of the original function. Why is that? Because the whole job of the inverse function is to take us back to the original inputs, right? So if the inputs here for the original function is everything that's greater than or equal to 5, then the inverse function has got to return values that are all greater than or equal to 5, right? So those two things have got to be the same. All right, then. So what we've got to do is we've got to find an expression for the inverse function, and we want to state the domain and range of that function. All right, so we have got the function, what is it? It is y is equal to e to the x squared plus 3. So let's go down. Y is equal to e to the x squared plus 3. Now, if we think about it, if we're trying to find the inverse function, right, the original function tells us the outputs y in terms of the inputs x. So the inverse function, what we want to do is we want to know what the inputs are in terms of the outputs, right? In other words, we want to rearrange the equation and make x the subject. So that's what we're going to do. And the way to do that is we're going to take the natural log of both sides. So we're going to get ln y is equal to x squared plus 3. And so x squared is going to be equal to ln y minus 3. And so x is going to be equal to plus or minus the square root of ln y minus 3. And the last stage of this, right, is conventionally we write the inverse function with the inputs as being x. So we just replace the y values with x. We've got plus or minus the square root of ln x minus 3. Now, this plus or minus, we got to understand it, right? Because it's not going to be both. It's going to be one or the other. So how are we going to figure this one out? Well, let's go back to the graph of that original function, right? The domain of this function, the domain of f is x is less than 0. That's what we're told in the question, okay? And the range is a set of all the possible y values. Well, all the possible y values have got to be everything that's that is, let's see, if x is 0, if x is 0, then we're going to get e to the 0 plus 3, and that will just be e to the 3. All right, so this y value here is going to be e to the power 3, and so the possible output values are going to be everything greater than e to the 3. So we're going to write that there. The range is y is greater than e to the power 3. Well, hang on. We just said for the inverse function, the domain is the same as the range of the original function, right? So the outputs for the original function is everything that's greater than e to the 3. So the inverse function, the inputs have got to be everything that's greater than or equal to e to the 3. And we also said that the range of the inverse function is the same as the domain of the original function, right? So if the inputs to the original function is everything less than 0, the outputs for the inverse function has got to be the same. It's got to be everything that's less than or equal to 0. So if we now go back, we want this function, the range of it, to be everything that's less than or equal to 0. So the only way that we can do that is if this guy here is negative, right? That's got to be negative. And what's the domain of this function? The domain is going to be x is, what was it? Greater than e to the power 3. So I think that's going to be everything there. We've got the expression, and we've stated the domain and the range, or I better state that the range. Range is f inverse will be less than 0. Okay. Yeah. So let me just double check that against the mark scheme. Always a good thing to do. Yeah. So negative square root ln x minus 3. Domain is x is greater than e to the 3, range is f inverse is less than 0. Okay, so that is all correct. That is an extremely hard question, guys. I think that is pretty tough. But you want to try to understand the functions, and really the key to doing that is basically kind of understanding diagrams like this. Okay, if you can get that, then you should be all right. Okay, then part C, hence find and simplify an expression for g of x. Well, let's try to think about this whole concept of a composite function, because in part A, what we've got is we haven't got g, we've got f of g, isn't it? Right? So what does f of g mean? All right, f of g. It means that we take the function g and we put it inside of f of x, right? That's what it means. So we take the whole function g, stick it inside f of x. Now, on a diagram, what that looks like is first we've got our input x, and it goes into the function g. And then after it's been through the function g, the output of that goes straight into the function f. And that then gives me my final output, which we'll call y. So this thing here in green, right, that thing is the entire function fg of x, right? So this thing is fg of x because it represents the whole thing. Now, we want to find out what g is, right? Now, we know what f inverse is. Because we learned that in the previous question. We learnt f inverse, so we know the step that takes us from here, right, back to there. Okay, so let's call the output of big G, let's call it capital Y, like that. So what we want to do is we want to find big Y is equal to G of little x, right? Now, we know that big Y is also going to be the inverse of this thing, right? So if I was to take my output Y, this one, stick it into the inverse function, what I should get is I should get big Y. So I can say, all right, big Y is also going to be equal to F inverse of that output little y. But hang on, that output of little y is the output of the whole composite function f of g. Okay, so actually what I'm really doing is I am taking the inverse of f of g of x. I know that's all quite complicated, right? But I think that you want to try to understand the steps. Okay, so I need ways of labeling it, right? So I've called this guy big Y because I want to say, look, big Y basically represents the output of g of x on its own. So is there another way to get to this value? Well, yes, there is, right? Which is to go through this route, which is to basically go from x straight through to the end here, which means we've gone straight through the composite function fg, and then to apply the inverse function like that, which will take me back to there, right? So if we want to go from here to here, right, which is basically defining the function g, the way we're going to do that in this question is we're going to go straight through the composite function fg and then go back a step f inverse to here, okay, which is what we've got here. So we've got to do the f inverse of fg of x. So let's state what those two things are. We just said that f inverse of x was equal to negative, oh my goodness, what was it? Negative the square root of ln x minus 3. And we are told in the question that fg of x is equal to, where was it? E to the power of 2x. That's e to the power of 2x. So what we want to do is, basically we're saying that g of x, big Y, is equal to f inverse of this thing here, fg of x, e to 2x. So I'm going to substitute e to the 2x into here. And so that's going to give me negative the square root of ln e to the 2x minus 3, right? So I've taken the x here and I've replaced it with e to the 2x. Now ln e to the 2x is just e to the 2x. So we've got negative the square root of 2x minus 3. And so I think that that should be our answer. I'm just going to check it against the mark scheme. Yeah, negative square root 2x minus 3. All right. Now, I in all the years that I've done this, to be honest, I don't think I've seen a harder question conceptually, right? There are some questions which are hard because you've got to work through lots of stuff. But this is a hard question in the sense that you really, really, really got to know what you're talking about. And it is going to distinguish the students who are like the A stars from the students who are aiming for 100% and top in the world. So it's a hard question. So on one level, guys, if you're just aiming for your A star, I would say don't sweat it too much. It's only 2 marks. But that being said, right, you want to try to understand it. This is a question that's really going to test whether or not you understand what's going on. And so in that sense, it's good. But for those of you who are definitely aiming, you want to get top, then this is the kind of thing where you need to be, on solid ground. And I think the way to do that is basically understanding diagrams like this, right? If you can understand diagrams like this, then you basically will understand functions and you should be able to get towards your answer. Okay, and I hope that was helpful, guys. And as I say, if you do like the videos, please like, subscribe, and share them with your friends. I hope to reach more people, and I hope more people can understand and enjoy this kind of math. Okay, so we're in question 11, the last question of this paper. In the binomial expansion of 2 plus a half x to the power of n, The first three terms in increasing powers of x are b plus abx plus 9/8 abx squared. Find the values of the constants n, a, and b. Well, okay, we're going to have to do the binomial expansion, aren't we? So let's write that out. We're going to have 2 plus x upon 2 to the power of n. And we're going to have increasing powers of x, right? So we're going to start with decreasing powers of the 2 term. So I'm going to write that out. I'm going to have 2 to the power of n, and then I'll have a 2 to the power of n minus 1, and then I'll have a 2 to the power of n minus 2. And corresponding with that, I'm going to have the powers of x upon 2, which will be x upon 2 to the power of 0, x upon 2 to the power of 1, and x upon 2 to the power of 2. And then lastly, I'm going to have my coefficients, which are nc0, nc1, nc2. Now, you're probably watching this and wondering, hang on, why didn't I just write it out all in one go, left to right? Well, I don't know about you, but I find if I do that, I make a mistake actually quite easily, right? Because there's so many numbers flying around. So I prefer to do all of the first term. So 2 to the n, n minus 1, n minus 2. Then do the second term, power of 0, power of 1, power of 2. And then do the coefficients, because then I find that I'm less likely to make a small slip. And small slips in this question are very, very irritating. All right, so we need to simplify this. NC0 is 1, because anything NC0 for any value of n is 1. 2 to the power n is just 2 to the power n. And x upon 2 to the power of 0 is 1, because anything to the power of 0 is 1. Okay, NC1 is n. 5C1 is 5, 6C1 is 6, 7C1 is 7. So NC1 is just n. 2 to the power n minus 1. And then here we've got x upon 2. And then we've got NC2. Now, I think I will probably expand that. So I'm going to use the formula for NC2, which will be n factorial over 2 factorial n minus 2 factorial. Now that's given to you at the front of the exam, I believe, right? So you should be able to use that formula. 2 to the power n minus 2. So we've got 2 to the power n minus 2. And then x upon 2 squared will be x squared upon 4. Okay, plus dot, dot, dot. Okay, now we need to tidy this up a little bit. So the first term, 1 times by 2 to the n times by 1 is just 2 to the power of n. The next term, right, well, we've got 2 to the power n minus 1 divided by 2. So dividing by 2 is the same as dividing by 2 to the power 1. So what do we do when we have got a to the x divided by a to the y? We subtract the powers, don't we? We do a to the power x minus y. So here we've got 2 to the n minus 1 divided by 2 to the 1. So we're going to be subtracting the powers again, right? So 2 to the n minus 1 divided by 2 to the 1 is 2 to the n minus 1 minus 1. Okay, so 2 to the power n minus 2. Okay, so sorry about the long explanation there, but, some people, find those small things actually to be the most annoying. So we've got n times by 2 to the power of n minus 2 times by x. Okay, now this thing here can simplify. Now, I've explained this on other videos. Let me just go down. If we've got 5 factorial over 4 factorial, what does that actually mean? That means 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Now, what's going to happen there is that all of the terms that are 4 or less are going to cancel off. So we're going to be left with 5. So 5 factorial divided by 4 factorial is just 5. In the same way, 10 factorial divided by 9 factorial will be equal to 10. And I don't know, 12 factorial divided by 11 factorial will be equal to 12 for the same reason, right? Because all the other terms are going to cancel off. Well, this also applies, right? If we were to have, for example, 5 factorial divided by 3 factorial. Right, so if we've got 5 factorial over 3 factorial, then that would be 5 times 4 times 3 times 2 times 1 on the top. divided by 3 times 2 times 1 on the bottom. And the 3, the 2, and the 1 all cancel off, so we're left with 5 times by 4. Okay, and in the same way, if I had 10 factorial over 8 factorial, I would be left with 10 times by 9. And if I had, for example, 15 factorial over 13 factorial, I would have 15 times by 14. So what about the case when I've got n factorial over n minus 1 factorial? Well, what's going to happen is all the n minus 1 terms are going to cancel off, and I'm just going to be left with n. Okay, now if you're really not sure about that, let me write it out in full. This is n. I'm going to subtract 1, n minus 1, subtract the next one, n minus 2. Keep going, keep going, keep going. And then on the bottom, I'm going to start with n minus 1. And I'm going to subtract 1, which will give me n minus 2. And then n minus 3, and so on and so on and so on. And what's going to happen? All these terms cancel off. Okay? Now, in the same way, if I was just to change this a little bit and say, what's n factorial over n minus 2 factorial, then on the bottom, I start at n minus 2, don't I? And so all of those terms will cancel off, and I'm left with n times by n minus 1. And that's exactly what happens here, right? So this is what's happening. So the term here, n factorial divided by n minus 2 factorial, is just n times by n minus 1. So let me get rid of that. So we have got plus 1 upon 2 factorial, which is 1 upon 2, times by n minus 1, times by 2 to the power of n minus 2, times by x squared, divided by 4, which is the same thing as 2 to the power of 2. That's dot, dot, dot. Okay. Now we can simplify this again some more, can't we? So this is 2 to the power of n plus n times by 2 to the power of n minus 2 x. All right, now we've got 2 to the power of n minus 2 divided by 2 to the power of 2, right? So we're subtracting. So we've got n minus 2 minus the 2, so it'll be n minus 4. And then we got another 2 here, which is 2 to the power 1. So we also subtract that. So we're going to end up with here the n minus 1. And then we've got 2 to the power of n minus 2 minus 2 minus 1, which is n minus 5 x squared plus dot, dot, dot. Now, I think that's about everything that we can do to simplify this. Now, we are told in the question that that is equal to b plus abx plus 9 upon 8 abx squared. So b, so this guy here, that's our b, right? This guy, the coefficient of x is ab. I think that was it? Yeah, ab. And the coefficient of x squared is 9 upon 8 AB, was that? Yeah, AB. Okay, so the coefficient of the constant, or just the constant term is 2 to the power n. AB is n 2 to the power n minus 2, and this thing here is 9 upon 8 AB. Well, I think we can start to solve this, can't we? Because we'll start with b is equal to 2 to the power n, and we can then say that AB is equal to n times by 2 to the power n minus 2. But hang on, we already know that b is equal to 2 to the power n, isn't it? So I can substitute into there. So call that whatever, equation 1, equation 2. I'm going to substitute equation 1 into equation 2. So I'm going to get a times by 2 to the power n is equal to n times by 2 to the power n minus 2. So I can rearrange that a little bit. So I'm going to get a is equal to n times by 2 to the power n minus 2 over 2 to the power n. And again, I'm going to be subtracting the powers, aren't I? So I've got n minus 2 minus n, which is just 2 to the power of negative 2, right? Because n minus 2 minus n is just negative 2. And 2 to the power of negative 2 is 1 upon 2 squared. So we've got a is equal to n times by 1 upon 2 squared, which is a quarter, which is the same thing as saying n is equal to 4 times by a. So we've got n is equal to 4 lots of a. We've got b is equal to 2 to the power of n. Okay, well, let's have a look at this one here. So we'll call this equation 3. We know that n times by n minus 1 times by 2 to the power of n minus 5, I think that's right, is equal to 9/8 of AB. Okay, well, actually, we already know what AB is. AB is this term here, isn't it, right? So why don't we just substitute that directly in? So we're going to get n bracket n minus 1 times by 2 to the power of n minus 5 is equal to 9/8 times by n times by 2 to the power of n minus 2. So if you're not sure about that, I saw this thing here, beg your pardon, is AB. And I know that that's AB, so I just decided to substitute it in. Well, that's nice because that just gives me one whole equation in terms of n. So actually, probably, to be honest, I should have started there, but never mind. Okay, let's cancel off. I can divide through by n. So n is gone, n is gone. And I think what I will do is I will also divide through by 2 to the power n minus 5. So let me just shift across a little bit. So I'm going to get here n minus 1 is equal to 9/8 times by 2 to the power of n minus 2 divided by 2 to the power of n minus 5. Okay, and again, I'm going to use the subtraction rule. All right, so I'm going to be subtracting these indices. I'm going to get 2 to the power of n minus 2 minus n minus 5, right? I'm going to do this nice and slow just to make sure that we're not making any mistakes, right? The classic error here is people will say, they'll forget this is minus minus, right? With the bracket. So we've got 9 upon 8 times by 2 to the power of n minus n is 0. Negative 2 minus minus 5 is positive 3. So we've got 2 to the power 3 there. And 2 to the power 3 is the same thing as 8, isn't it, right? So actually what we've got is we've got 9/8 of 8. So that's going to cancel off the 8 and the 8. And so in other words, what we're left with is n minus 1. N minus 1 is equal to 9. And so n is equal to 10. Okay, well, if we've got n is equal to 10, we can go back and find the other values, can't we? Because a will be equal to n upon 4. So 10 upon 4, which is 5 upon 2 or 2.5. Okay, so it's 5 upon 2. And b is 2 to the power of n. So b will be equal to 2 to the power of 10. Okay, whatever that is, I can whack it into a calculator. 2 to the power of 10 is 1024. So let me write that out. So a is equal to 5.2. B is equal to 1024, and I get that n is equal to 10. Those are my final answers. And what I'm going to do is I'll check the mark scheme, because it's always a good idea. And let's see if that's right. Where is it? Oh, I can't find it. Just give me 1 second. Okay, well, that's very odd, guys, because the mark scheme that I've got, and the mark scheme I've got direct from Cambridge, actually doesn't have the answers for question 11. So I think they must have made a mistake when they published. So that's pretty strange. I'm reasonably confident in that answer. I think with this kind of question, right, it is actually pretty hard. All right, I mean, I think this is quite hard. There's a lot of algebra here, but I think the key value is basically patience. You just need to be nice and calm and collected. The way I do this, of course, I'm slowing down because I'm explaining it to you on the video. But actually, if I was doing this for real in an exam, I would basically write out every single line exactly as I've done it here. Because when you're trying to do too many operations in your head or on your calculator, it's so easy to make a small mistake. And small mistakes in this kind of question are really costly. So what I recommend you do is you do exactly as I've done it, which is simplify, you know, one step, one step, one step. Make sure you do each of those lines nice and meticulously, so that, you know, by the time you get to the final line, you're reasonably confident that you haven't made a slip, okay? Or if you have made a slip, it'll be easier to identify. So guys, what I would say is be patient, be calm, just work through this question nice and slowly and progress your way towards the end. Okay, now hoping these videos are very helpful. If you're finding them useful, please leave a comment, please like and subscribe and share it with your friends and fellow students. Bye-bye.